All right, here we go. Okay, so here's what you need to know about tangent, right? Be able to sketch its parent function, y-axis, x-axis. We count by half cycles instead of quarter cycles. So tangent passes through the origin with an inflection value or an axis point, if you want to call it that. And then the next point is the vertical asymptote. So we count by pi halves. So that's 1 pi halves. And now we kind of keep that distance 2 pi halves, which is pi, 3 pi halves, 4 pi halves, which is 2 pi. And then we'll go the other direction, right? Same distance. Here's negative 1 pi halves. Negative 2 pi halves is negative pi. Negative 3 pi halves. And then negative 4 pi halves is negative 2 pi. And all we got to do is put our marks down. So all we're going to do is alternate from axis point or x-axis point, x-intercept, which is the inflection value, and vertical asymptote. So vertical asymptote here, axis point there, asymptote here, axis point there, then so on and so forth. Asymptote, axis, asymptote, axis, so on and so forth. And now tangent is an increasing function. So it's going to be increasing, curving downward, concave down to the left, and then increasing concave up to the right. So we want to make sure that these now are the same steepness. And we try to launch through at a 45-degree angle, because that's essentially what tangent does. It launches through at a 45, where x cubed, which this looks like x cubed, we talked about Friday, actually goes horizontal there. Okay, so let's talk about its characteristics. Domain, is it all real numbers? Yeah, not obviously, right? There's vertical asymptotes. So do the vertical asymptotes happen at regular intervals? They do. So instead of saying which values don't work, it's easier for the domain to say which values don't work. And then by default, all the others will work. Kind of like when we divided by 0, we said x can't equal something. So let's go ahead and do that. It's the set of all x's such that x shall not be, okay? So we're doing this in set builder notation. It's going to be really hard to list the domain in roster notation or an interval notation because there's so many infinite discontinuities. So all we have to do is say x can't equal, and you pick your favorite vertical asymptote. My favorite one is pi halves because it's the first positive one. So x can equal pi halves. So there's where the first one exists. And then all you have to do is say plus multiples of how often they occur. They do occur at regular intervals, right?
Plus or minus.
Well, we're going to say multiples of, which is integer multiples of. You could say plus or minus, but I'm going to let the the n be an integer, so we can use -1, -2. So how far away are they from each other? One what? 1?
Yeah, just one. So it's like
Pi halves plus 1 is 2 plus pi halves. That's not 3 pi halves.
no, if you were to put it
1.
in decimal, then
1.
now if you were to put it in decimal of like 2/2, and then combine them, then make 3/2.
No. No, 2 plus pi is not 3.
Well, what about the invisible one in front of pi?
That's 1 pi.
Yeah, then just add the 2 to the 1.
Whoa, it's Monday, isn't it?
Yes.
You okay with that?
I'm still on Monday brain.
Are those like terms? No. Now, if that were 2 pi, that'd be good, right? Yeah. So anyway, how far apart are the vertical asymptotes from each other? Pi. Good. We said that on Friday that the primary cycle of tangent is this one here, which occurs between -pi halves and pi halves. That's the main branch, or the main cycle, because it's the one that's closest to the origin, and it straddles. So the period is pi, right? So these occur every multiple of pi. So we'll just say pi n, where n is an integer, because if we don't specify n being an integer, you might think it could be like 1.3 or 1.5. Okay, a real number. By default, it's real number. So pi halves plus pi n, where n is an integer. So when n is 0, we get pi halves. When n is 1, we get 3 pi halves. When n is 2, we get 5 pi halves. When n is -1, we get negative pi halves, so on and so forth. Okay. Now that brings us to the period. The period, of course, is pi, whereas sine and cosine was 2 pi. So tangent has 2 complete cycles as we go once around the unit circle. Pretty important. All right. What's the range? Excuse me. Yeah. You could say it's the set of all y's that is in the interval from -infinity to infinity. Or you could say the set of all y's such that y is an element of the real numbers. Or you could just say double bar r, right? It is all real numbers. That was the domain of sine and cosine. Sine and cosine's range, though, stood between -1 and 1. These cover all the values from -infinity to infinity. All right, what else? How about symmetry? Any symmetry going on here? Does it have y-axis symmetry? Does it have the seal symmetry where you fold it? No. Does it have rotational symmetry where you turn your iPad upside down when it's on screen lock? Does it look the same? You didn't even turn your iPad upside down. Did you do a headstand? I missed it. Okay. Does it look the same upside down? It does. It does. So what types of functions do we call those guys? Origin symmetry. It can have x-axis symmetry or it wouldn't be a function, right? Only the x-axis has x-axis symmetry and passes the vertical line test. So what type of function do we call those with origin symmetry? Origin symmetry. Y-axis symmetry are even functions, so these are odd functions. Yeah. So tangent is an odd function, which means, look, which of the other two that we already studied was an odd function, sine or cosine? Sine, very good. Sine was an odd function. So just like sine, tangent of negative inputs, do we bring it up front or forget about it? No, we bring it out front.
I'm still on that Monday brain. I should have come in, but I still.
Oh.
It is still Monday.
Yeah, we bring it out front. For even functions like cosine, we forget about it. Yeah, I guess. All right. Okay. Let's see. What else? What else? Is this function 1-to-1? Remember what 1-to-1 meant? Like e to the x was 1-to-1, natural log of x? It's not. Why? Well, it passes the vertical line test.
The vertical aspect, it doesn't have every y value doesn't have a.
Oh, that would be domain of all real numbers. Remember, for 1-to-1, that means every x has just one y value, but every y value also has just one x value. And is that true? No, every x has one y value, but this y value right here, it has infinitely many x's associated with it, right? So it's not 1-to-1. Okay, it is not 1-to-1. But is it monotonic increasing? Monotonic increasing means increasing and increasing only. Sine and cosine were increasing and decreasing, right? Up and down and up and down. Does tangent go up and down and up and down?
No, it just either goes up or down.
We read a graph from left to right. We read a graph from left to right.
I'm on Monday right still.
This graph is only going up from left to right. Is it going up and down? No, it only goes up or down. But it is monotonic increasing over its domain. So if you hop on the graph and go to the right, you're only going uphill. Now, it does kind of do like the Pac-Man escape thing, right? As it goes up off the screen towards infinity, it comes back in the bottom, right? And starts anew, like Pac-Man exits, on the right to come back in the left, if you've ever played Pac-Man. This one does it vertically. But it is only going uphill, okay, from left to right. So that's kind of interesting because sometimes functions that are monotonic increasing are also one-to-one, like e to the x is monotonic increasing and it's one-to-one. The difference here, though, is the domain is not all real numbers. So if a function were monotonic increasing for all real numbers, then it would have to be one-to-one. But here's an example one that is monotonic increasing, but it's not one-to-one. It fails the horizontal line test. That's what that means, not one-to-one. If you want to remember that, it fails the horizontal line test. E to the x and natural log of x are both one-to-one. Okay, anything else we want to say about this function? It's purple. Very nice, very nice. Purple. Borat would like it, right? Brady, any other comments about it? No, okay. Probably safe to. I was curious if you noticed anything we didn't notice about it. Yeah. All right. So you got that memorized. Here's the easy way to remember vertical asymptotes. Vertical asymptotes at odd pi halves. Vertical asymptotes at odd pi halves. So the same values of x that are not in the domain are the same values of x that equal the vertical asymptotes, right? This function has vertical asymptotes at x equals pi halves plus pi n. But because they're vertical asymptotes, they're not in the domain and x can't equal them. Does that make sense? X does equal them, but they're not in the domain. Okay, they only equal them as vertical lines that represent imaginary lines that are vertical asymptotes. So odd pi halves, that's an easy way to remember it. We don't write it as odd pi halves if I ask you for the domain. We write it like this, pi halves plus pi n, written as an integer. But to remember odd pi halves, 1 pi halves, 3 pi halves, 5 pi halves, what would come next? Look, he's redeeming himself, right? Getting into Tuesday brain on a Monday morning. Nice, nice. All right, let's go ahead and sketch some transformations of these fellows. Example 3, okay? Because we just kind of did example 1 and 2 combined. All right, so 2 tangent of x plus 1. First of all, what's the parent function? Tangent, yeah. Is it in standard transformation form? Yeah, very good. Is that x plus 1, is it inside or outside? It's outside, right. If you intended it to be on the inside, you would have had to have put parentheses there. So this is an a value, as Brady already said, and a d value. So what does the 2 do to any function?
A multiplier and a movement up.
Well, it's a multiplier, so it's a dilation. So it's a stretch or compression. Stretch vertically or horizontally. Vertically, because it's in front by a factor of 2. Now, for sine and cosine, we call it the amplitude. We don't really call it the amplitude here because tangent is not a wave function, but it will make it twice as steep, okay? And then the plus 1 does what to everything?
A vertical shift.
Vertical shift up 1 unit, right? So what's gonna happen to these axis points, which are the inflection values that normally occur on the x-axis?
It's gonna move up 1.
They're going to move up 1, right? And then the graph is going to be a little bit steeper, okay? And since we didn't shift it and we don't have a b value, the period should still be what? Pi, right? So we still count by what? Pi halves. Good. For tangent, the period is pi, and we count by pi halves. So we can go ahead and set up our axes right away. But what I'm going to do is right here, I'm going to put a 1. Now, I'm not going to draw a horizontal line going all the way through because I think it's going to be easy not to do that. So I'm going to have a dot there, and then here's pi halves. There's my vertical asymptote. And then the next one at pi, I'm going to have a dot. And now at 3 pi halves, I'm going to have a vertical asymptote. Negative pi halves, the critical values are still the same as what we just did. And then negative pi, I'm going to have a dot, but I'm putting it up here at 1, right? And then out here, I have negative 3 pi halves. Okay. So I took care of the +1, just like what we do when we're sketching a sinusoid. We draw that sinusoidal axis first. It's the last thing we do transformation wise because it's the d value that's added at the end, but it's the first thing we do when we're sketching it, right? So now all I got to do is draw it twice as steep as normal. Does this look twice as steep to y'all?
Yes.
Thank you. Have we ever really shown vertical stretches and compressions on our graphs? No, because it's hard to quantify it, right? We can describe it from the equation. It was like, oh, it was a vertical stretch by a factor of 2 from the original, but we don't really show it. So as long as your inflection values are there at y = 1, you're good. So really, you could try to go through the origin with the slope of 2 instead of a slope of 1. But what does that look like? Yeah, your guess is as good as mine. Okay. All right. So there we go. What's the domain of this function? Did the domain change? No, it's still the set of all x such that x cannot equal what? Yeah, good. Pi halves plus pi n. Now we have to put that n as a what? You have to put that it's an integer because the default group of numbers that we use this year is real numbers. And n has to be a whole number or a negative whole number, which are called the integers, and we represent that by z, right? Zintegers or integers. Z, z. All right, did it change the range? No, it's still double bar. Arr. Arr. Are you ready, kids, for a pajama party? All right. Oh, yeah, Captain. Hey, what's this fella? Look at this. What's, uh-oh, cotangent. Have we met that guy yet? No. Hi. All right, we better meet cotangent. Let's come up here to example 2. Let's retreat. Retreat. Well, remember that cosine and cosine were almost the same? They were just shifted off of each other by a phase shift of how much? You remember?
Depends on what you're going with.
Well, sine and cosine, that's what I'm going with. Well, the period, just regular sine and regular cosine. By what? Pi halves, good. Sine and cosine were pi halves off. Phase shift off from each other. And I mentioned it early on, why they're called sine and cosine. Pi halves is the same as 90 degrees, right? What does the co and cosine actually mean? Do y'all remember? Cody is a good guess. Contamination is also a good guess. Constriction, not a bad guess. Constipation, cobalt. No one remembers? What if I told you it has to do with 90 degrees or pi halves radians? Complementary, thank you. Nice. They're called complementary functions because they only differ by 90 degrees, just like two angles are complementary if they only differ by 90 degrees. They add up to 90. So guess what tangent and cotangent are? They're complementary functions, and their graphs then only differ by 90 degrees, or how many radians? Pi halves. So nice. He is making up for it. Yeah. Get you some mid-morning brain. Negative pi halves, negative pi, negative 3 pi halves, negative 2 pi. Yeah, if we're off by pi halves radians, tangent normally has an axis point at the origin, right? Well, now it's going to be at pi halves. Tangent normally has a vertical asymptote at pi halves. Now it's at pi. And now we alternate the exact same way. Now, there's one little thing that's different about cotangent aside from the vertical asymptotes are now multiples of pi instead of odd pi halves. It's not an increasing function. Let me show you why. Pick a light flavor here. Light flavor. Yum. How about yellow? Yellow kind of doesn't show up. Let's go ahead and draw a tangent in here, okay? Let's just draw a tangent in there. Oops, hang on. See, that's what happens when you try to draw when you don't have your vertical asymptotes in place. If we draw a tangent in there, it looks like this. Hello? Hello? Hello, 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 hello. Oh, hi. So the yellow, hi, axis, low axis, Haley. Hi, Haley, axis, low, Haley. Tangent is not only the cofunction of cotangent, complementary off by pi halves radians, but remember, it is also the reciprocal, yes? Reciprocal, reciprocal, like precal, reciprocal. So super reciprocalifragilisticocious. Let's go ahead and take the yellow y values and plot their reciprocals, shall we? Okay, let's look at tangent at the origin. What is the tangent value at the origin? 0? 0. Well, what is the reciprocal of 0? DNE, because it's some type of infinity. And how does infinity manifest on a graph? Vertical asymptote. Yeah. What is tangent of pi halves? DNE, because it's some type of infinity. What is the reciprocal of infinity? 0. So that's why cotangent has an axis point where tangent has a VA and vice versa. Now, let's think about some other points. Let's think about tangent right there close to the origin, like right here. Let's say that that value is 1/2. What's the reciprocal of 1/2? 2, which is up here. Let's get even closer. What about right here? Let me use a slightly dark. What about right here? Let's say the y value there is 1/100. What's the reciprocal of 1/100? 100, which is way up here. Let's look right here where tangent is 1. What's the reciprocal of 1? 1. Its own reciprocal, right? And how about right here where tangent is 100 or 50? What's the reciprocal of 50? 1/50th down here. Oh, if we connect those blue dots now, it looks like this, don't it? Which makes tangent not an increasing function, but a what? Decreasing function. So you could keep doing that all the way through, but I'm not gonna. I can say that I did, but I ain't gonna. All right? Gonna. G-U-N-N-A. Gonna. There you go. There is cotangent. F of x equals cotangent of x. Do you have to know that function? I promise you, you don't have to know tangent moving forward. But in this section, I would like for you to know cotangent. It's easy to get from the graph of tangent. Yes, yes? Yes, yes, right? All you got to do is remember it's the same critical values. They're just offset. Cotangent has a VA at 0, and tangent passes through 0. You can remember that because what's tangent of 0 from all our unit circle quizzes? 0, right? And what's cotangent of 0 from all our unit circle quizzes? D and E. And for tangent and cotangent, if you know just one critical value, namely at 0, you know what all the rest of them look like, because it's not high axis, low axis, high axis, low. It alternates inflection value asymptote, or axis point asymptote, axis asymptote, axis asymptote, axis asymptote. Yeah, asymptote. In Precal, by the time you get out, you should know the difference between your asymptote and a hole in the graph, right? Yeah, okay. So let's look at its characteristics. What's the big D domain of cotangent? It's not all real numbers. It's a set of all x such that x ain't equal to what? Find your favorite vertical asymptote. Pi will work. 2 pi will work. 157 pi will work. I like 0. My hero, 0. Have you heard that song from Schoolhouse Rocks? Yeah. Plus multiples of how often they occur. How often do they occur? Pi. So pi n, where n is a what? A integer. Oh yeah. Now, we can simplify that, can't we? What is 0 plus pi n? It's just pi n. Yeah. So for tangent, you need to put pi halves plus pi n, because pi halves ain't 0, right? But for cotangent, you could just put pi in. X can't be pi n. All right. So this one has VAs at multiples of pi, whereas tangent has odd pi halves. Cotangent has even pi halves, if you want to think about that, right? Just multiples of pi. What's the range? All real numbers. Yep. Any symmetry going on? Y-axis, does it have the clapping seal symmetry? Y-axis symmetry? Or. No. But does it have do a headstand and look at it upside down symmetry? Yes, which means it's what? If it has origin symmetry, which means it's what type of function? It's an odd function. Does that make it peculiar if it's odd? Not necessarily, but sometimes, yes. So here we know then the consequence of that is cotangent of negative x is, forget about it or bring it up front? Bring it out front, right, Brady? Yeah. Good. Now, this one is not 1-to-1. It fails the horizontal line test, but it is monotonic. Monotonic is sometimes replaceable with the other word strictly. Okay, it's an adverb. Monotonic or strictly what? Decreasing. Yeah. It's a decreasing function. Tangent is increasing and passes through the origin. Cotangent is decreasing and has a VA at the origin. One last thing here off to the side. What is the period or wavelength? How often does this graph repeat? Pi. Just like tangent, it repeats every pi. So when we graph it, we count by what? Pi halves, half cycles. We don't count by quarter cycles. We don't count by motorcycles. Vroom, 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 vroom. All right. What? Unicycles. As long as uni equals pi halves or half. What? Tricycles. Now we could do example B. Aha. Quadricycles. Cars. Negative cotangent of -1. This is an A value, and this is a D value. What does a -1 for an A value do? Does it stretch or compress it? No, but the negative flips it across the X-axis. And we say flip when we're among friends outside of class, like at a math party or in a bar, like a juice bar or a hookah bar. Okay. Normally we say reflect. So it's going to reflect it across the X-axis, and then it moves down one, right? Well, let's look. What happens when you reflect cotangent across the X-axis? Let's do that in red. It turns it into a what? It turns it into an increasing function, right? So you can actually, look at this. You can actually turn any cotangent graph into a tangent equation, can't you? All you got to do is not only do the phase shift, but how do we make it from decreasing to increasing or vice versa? Put a negative out front. Oh, that kind of opens the door for writing equivalent equations, doesn't it? Yeah, it does. So, oh yeah, let's go ahead and graph this puppy, right? It's National Pet Day. Y-axis, X-axis. The critical values are the same, right? So we got 0, 1 pi halves, 2 pi halves, 3 pi halves, etc. Make sure they're spaced evenly, right? And then in negative land, we got negative pi halves. We go a little bit further in negative land here. For sine and cosine, we didn't. We just had one negative value. But because tangent kind of straddles, it's nice to have, you know, a few more negative values here. But you could have just at least one negative value again. All right, now I'm going to put my axis points not on the x-axis, but down at -1. I'm going to call this -1. Do yourself a favor and label it below where you marked your values, okay? So you don't write on top of them. And now what we got to do is put our marks down. Let's start at the y-axis. Do we put a dot or an asymptote? An asymptote, right? And then we put a dot. So again, tangent, cotangent, a little bit easier to graph, I think, because you only need 1 point to figure out all the rest, okay? For cosine, you only need 1 point, either a high or a low, but for sine, you needed 2, right? Because there's 2 ways to go from an axis. Pi, axis, low, axis, pi, Haley, low, axis. Haley also starts with H, right? Like high, right? Pi, axis, low, axis, Haley, axis, low. All right, and now all we got to do is connect the dots, showing the change in the curvature at the dots. And is it increasing or decreasing? Increasing or decreasing? Well, it was cotangent. However, it's a negative. So it flips, right? It becomes, well, yeah, it becomes possibly a tangent. If we want to write the equation, we can. I think we will. Oh, yeah. It becomes increasing.
Basically, it becomes tangent, but C's plus.
Yeah, let's go ahead and write a tangent equation for it. It's just going to be tangent of x. It's going to be -1 for sure, right? But we don't need a negative in front of tangent, do we? But I do need a freaking phase shift, don't I? Yeah, I do. So let's put parentheses around there and parentheses around there. Just like for sine and cosine, if I can get to the point that tangent normally has at the y-axis, I've got it. What does tangent normally have on the y-axis? A dot or a VA? A dot. Do we have any dots or axis points labeled, inflection points labeled? Yeah, we got 4 of them. So let's shift over to the positive pi halves. What's it going to be in my equation? Minus pi halves. What if I messed up and oopsidentally put plus pi halves? Would it work here? Oh, yeah, you sure will. Ooh, that was a close call. There you go. Hey, let's come back over here to letter A and write an equivalent equation now in terms of cotangent. Okay, so for cotangent, the A value is still 2, right? But to get it to flip, I need to do what with it? Negative. So -2 cotangent. I'm going to have a phase shift. So give yourself room to put your phase shift, and it's still +1. Okay. Now all I got to do to make it a cotangent is shift over to the behavior that cotangent normally has on the y-axis, which is a what? A VA or a dot. You're the one who told us originally that it didn't, right? When you made the connection, now you forgot. You're regressing to Monday brain, or you're moving forward to next Monday, which is Easter Monday. We have Friday and Monday off. Yeah. Oh, yeah. Yeah. Clap. Clap for not being in school? Seriously?
It's because we have more time to do math.
Oh, there you go. Maybe you get some math in your Easter basket. Pi halves, right? Pi halves. Cotangent normally has a vertical asymptote on the y-axis. So let's do x minus pi halves. Oh, Brady, that works too. Okay. Now, it shouldn't be surprising that without changing the period, we're only shifting tangent and cotangent by pi halves. Because pi halves is the same as 90 degrees, and co stands for complementary, not constipated. Confident. Okay. All right. All right. How we doing? We got 5 minutes left.
No, I think I'm kind of seeing a pattern here.
Good.
Just,
That's what mathematicians are good at.
I think it's more like you reverse the A value sign.
Should we do one more? Let's do one more. Let's do one more. Let's do letter D. Let's just jump to letter D. Is this one a standard transformation form? No, no. So let's put it into standard transformation form. We got to factor out a 3. So it's x minus pi 6. Close, close. Got it. Got it. Now, there is a B value, isn't there? So that is going to compress our graph by a factor of 3. Is that going to affect the period? Yes. So the period is going to be what now? If it used to be pi, and now it's 3 times narrower, pi thirds. Good. So here is the formula for tangent and cotangent to find the new period. It's not 2 pi over b like it was for sine and cosine. It's pi over b. Pi over b. So our period here is pi thirds. And what are we going to count by? What's our half cycle counting interval? Pi 6. Oh boy. And look, we picked the graph up and moved it right. Pi 6. That's one critical value, isn't it not? All right. So we could go straight to our graph. Good. Did we shift it up or down at all? No. So the axis points, the dots, if you want to call them that, the inflection values are still on the x-axis. It's going to be twice as steep. Do we show that? Nah. Let's go ahead and lay down some tracks, shall we? We know 0 is going to be 1. Where's the next one? We're counting by what? Pi 6. So 1 pi 6, 2 pi 6 would be pi thirds, 3 pi 6 would be pi halves. And now we go to the left, negative pi 6, negative pi thirds, right? That's enough. All right. And now let's think about it. Cotangent normally has a vertical asymptote on the y-axis. But wait, we pick that vertical asymptote and move it right. How much? Pi 6. So now there's a vertical asymptote at pi 6. And once you have the vertical asymptote, you know how everything else falls into line, right? Goody, goody gumdrops. There's no vertical shifts, so we have them there. And now all we got to do is draw it what? Increasing or decreasing? Decreasing, because it's a positive cotangent. There you go. Now the last thing, let's write an equation in terms of tangent, shall we? What do we have to do to turn it into a tangent? Well, we got to flip it, right? So instead of 2, it's -2, tangent. And the b value is still 3, but now all I got to do is shift over to what tangent normally has on the y-axis, which is a what? A dot or a VA? A dot. Doesn't it already have a dot there? Yes. So we don't have to shift it at all. By scooching it right pi 6, the cotangent, we offset it by half the cycle. Okay, so there you go. We're done with tangent and cotangent. Tomorrow we'll meet cosecant and secant. Okay, and you're gonna love those fellas. They're squirrely. Enjoy the rest of your pajama day. Enjoy the rest of pet day. Enjoy the rest of civil rights day, and enjoy the rest of Carla Ford and Jeremy Clarkson's birthday. Okay, and Monday. Tomorrow is heavy metal rock hero. Thank you so much. My favorite flavor. Y'all have a super day. Don't forget powder puff preliminaries after school and quiz bowl in the library.